So this video will be note taking, examples of potential energy, kinetic energy. Pause the video, get these into your copy and just jot down other types of energy: heat energy, nuclear energy and chemical energy. You won't be dealing with these in the applied maths course, so pause the video, get these notes in. So just this is what my copy would look like if I was taking notes at this point. Get it in maybe different colors, put some bubbles around it, just write down everything you need to write down to understand exactly what energy is. Here's the definition of potential energy, just with the example of the stone and holding the stone and its ability to do work, that it has potential to do work. You should never forget what potential energy is. And if we think with potential energy, it's at rest. With kinetic energy, like a car moving along, it's actually going to come to rest. So one is starting at zero and getting faster, and one is moving it with speed and coming to rest. So the difference between kinetic and potential energy. So let's try and measure potential energy. So let's take this stone. Let's say it's on the edge of a wall, and here's the height of the wall, and here's the ground. Let's call the height of the wall h. So this stone, it can do some work, and work is equal to force times distance, as we have seen before in applied maths. We can call distance s, but in this case we have the distance here and we're given to it, it's h. So distance we can call h. This is what we're going to use within this formula for potential energy. And force, we've seen before when we're measuring things going down, we call it mg. This is the gravitational force pulling this object towards the center of the earth. So ma we could start with if you wanted, like the book does, and call a acceleration, but that's why this force will be m by a by h, which turns out to the formula that we use in the tables, which is mgh for what I'm going to call from now on P, potential energy. Now let's look at measuring what we call K from now on, kinetic energy. Come up with the formula here. So we have a car, it's traveling along. It's going to come to rest, let's say, at this point here. So what can we say when it comes to rest? We can say that the final velocity is 0. It has an initial speed. It's coming to rest, so the acceleration is going to become negative, and it's going to cover a distance of s. This distance here, we could call it h to begin with. We're going to call it s, it's s in the formula. So when we have vu, a, and s, we can apply this to the formula v squared is equal to u squared plus 2as. So 0 is equal to u squared. The s didn't appear. And we're going to have a minus here. Minus 2 times a, if I can put in g, times s, so I can write 2as is equal to u squared, and I was just going to say I can use g when we're coming down towards the center of the earth, but I should write a here, minus a. So let's look at how this will help us, because if we apply the work done being forced by distance for this car, we can then equate two things or replace one thing with something else, and we can come up with a formula for kinetic energy. So the force here is its mass times its acceleration, and we have the distance, which we're calling s. So the work done is mas. Now there's no m down below, but there is. If you look here, there's an as. So what would as be equal to? As is going to be equal to u squared over 2. If we divide across by 2. So therefore, what we end up with is u squared over 2, which can be also written as a half mu squared, which is my definition or my formula for kinetic energy and how to measure kinetic energy. And when v is the velocity of this object that we're going to be looking at, this kinetic energy formula becomes a half mv squared. So let's move on and look at some questions in relation to these.